Okay, thanks. So probably we'll nix the applications, which I'm a little sad about, but I hope you can just imagine where it's going. So here's what happened last time. There's not very much new pink stuff. So, well, 2 times ago, there was this assertion that infinity categories can be identified as a certain full subcategory of sheaves on the site of stratified spaces, the ordinary category of stratified spaces. And you can characterize exactly what the essential image is in terms of geometric descent, essentially. But don't confuse that with this descent being with respect to a Grothendieck topology, but just satisfying geometric conditions. And I gave 2 examples last time. One was, so if for M a smooth manifold, you can, yes. For M a smooth manifold, you can construct this Ron of M. It's some I'll say improved version of the Ron space of M, if you know what that is. But here it is if you don't know what it is. It's the sheaf on stratified spaces that assigns to every stratified space K this space. And I encourage you to ignore the delta bullet part. That's just to make it a space. Otherwise, it looks something more like a set or maybe a groupoid. And it's a point in that space is a constructible bundle over K, so long as its fibers are finite. So this is just like, think of it as just a finite sheeted cover of K, but stuff can happen to the fibers exactly according to the stratification of K. So it's something like a finite sheeted cover of K together with a proper embedding of that into M. So that's the Ron of M. And I could have mentioned this last time. So there's a forgetful map where you just forget this proper embedding, and all you remember is this constructible, this finite to 1 constructible map to K. And that gives you a map to the category of base finite sets op, because the category of base finite sets op exactly classifies these finite to 1 constructible bundles. If that's not obvious, that could be an exercise session type thing.
So it's the Ron of a point? It's not
This is not an equality. There's just a forgetful map.
I can restrict, can't I, Ron M to Ron of a point?
Oh, there's a functor. So this I've described it as something over here. It's a fact that it lies in here that I haven't said anything about. And therefore, I can identify it as an infinity category. So that, to me, is an infinity category. And there's a functor of infinity categories to finite sets off. Does that address what you were getting at?
What is Ron of a point? If M equals a point.
Oh, yeah. Then Ron of a point has 2 objects. There's empty set. There's the empty subset, and there's the point subset. And there's a map between them. And that's it. So that this lies, in that case, this is the inclusion of that subcategory. There's this other example that's by far the most important example for me. This is why this was developed, is bun. So this is the object over here, a priori, that classifies constructible bundles. If you write that down in terms of expressions, it's this assignment. It assigns to every stratified space the space of all constructible bundles over it. And a theorem, which is among the hardest things I've ever been involved proving, is that thing that you can write down easily in here lies in this subcategory, and therefore is an infinity category. So bun is an infinity category. And its underlying groupoid, underlying space, or underlying infinity groupoid, is the disjoint union over isomorphism classes of stratified spaces of B aught of that. So in particular, sitting inside of there is a bunch of components, is B diff of smooth manifolds. So this is a gigantic thing.
Now is this out the discrete group out? Or
No, it's out in curly strat.
Okay.
Yeah.
So it's in curly out.
Yeah. That's a subscript. And then the morphisms of bun are constructible bundles over the one simplex. The source and target is given by restricting to the two endpoints of the one simplex. And last time I mentioned there's 4 classes of morphisms. I phrased it in terms of monomorphisms from things, but I really think of that as classes of morphisms that are stable under like equivalents of morphisms. And one class is called closed. Those are the constructible bundles over the one simplex that you obtain from mapping cylinders of inclusions of closed unions of strata. And it's actually the reverse mapping cylinder of such. Likewise, there's creation morphisms, and that's what you get when you take mapping cylinders of just proper constructible surjective maps. There's 2 other classes of morphisms. There's refinements, and there's open embeddings. And in fact, these 4 classes of morphisms generate bun in a very interesting way. They do not form a 4-fold factorization system on bun. There's some interesting interaction, in particular, between creation and refinements, which makes this thing not a Burnside category, if that has meaning to you. So let me just write down some small modifications of bun that I was going to do in this lecture anyway. So another example is I just put a prescript C for compact. It's where it's just like bun, except I inserted the word proper. So this map is proper. In particular, the fibers are compact, and there's no like open embeddings. It excludes this class of morphisms. Another example is bun less than or equal to n, and that's what you get when you bound the dimension of the fibers by n. So bun less than or equal to 1 is precisely base finite sets op. Or bun less than or equal to 0. And then you can mix these at the same time. C bun less than or equal to n, you can imagine. So continuing with the review of last time, there was the construction of the tangent constructible bundle. It was the universal, or the unique section of this thing, which is obtained by a Groton deconstruction from the functor from the opposite of strat, where the maps are those that are constant rank stratum-wise, to categories given by homming out of exit path categories into this interesting infinity category curly vect. So this is the Groton deconstruction of that, and that was all designed precisely so that the tangent constructible bundle can be described somehow functorially. And it's described as the unique section satisfying these 3 points. The first is that it sends open embeddings to Cartesian morphisms, which is to say that, well, given any map, U to M, you get this map, df, from the vector fields on U, from the tangent constructible bundle of U to the pullback one for M. And the condition is that when the F is an open embedding, then that map is an equivalence. The second requirement is that this section sends blow-up squares, which are square diagrams in here, to pullback squares up here. And the third requirement is that this is all standard on Euclidean spaces. And I gave this example to kind of feel what this thing is. So in the simplest example of a stratified space, if you have a properly embedded smooth submanifold of another, W inside of M, then so whatever this tangent constructible bundle is, it's a functor from the exit path category of this thing to curly vex. And the exit path category, in this case, its underlying groupoid has two components, it separates into two parts. One part is just W, and the other part is the complement of W. And on W, this is just nothing other than the regular old tangent bundle of W. And likewise for M without W. So the remaining data to specify what this functor is to say what it assigns to a morphism in the exit path category, which would a non-invertible morphism, which would have to go from W to the complement of W. And that space of morphisms from W to the complement is the same as the unit normal bundle of this embedding, which I'll call the link. Being the unit normal bundle, it sits inside of the complement of W, and it projects to W. Those are two maps, gamma and pi. And so to say what this functor does, it's to give a map of vector bundles over this unit normal bundle from the pullback by pi of the tangent bundle of W to the pullback of gamma by gamma of the tangent bundle of M without W. And it's given by this map. You choose a splitting of the projection from the unit normal bundle to W. That's a contractible choice, which is why it's just the way to go to do this all at once if you want it to be, in any sense, homotopy coherent. So you choose a section there to there. You include this as the zero section inside of the link, or the tangent bundle of the unit normal bundle across R, and then apply the differential of the embedding of the tubular neighborhood. This is actually an isomorphism to that, and that's everything. So that was last time.
Sorry, I just fell a little behind there. When you write link, link is one component of this axis W.
Link is the space of morphisms in exit from W to M. So what's the fact that the space of morphisms in this exit path category is again,
The space of non-identity.
that's right, is again not just the space, but it comes from a smooth manifold, is extremely convenient for arguments, because then you can use induction and stuff. And that's why all the regularity was around. Okay. So continuing, we want to say what a framing of a stratified space is. So toward that end, let me just give this quick definition. So there's another constructible vector bundle. Call it epsilon for like the trivial bundle dim. And this is so easy. Let me just say, so this is the dimension constructible bundle. And this is given by the functor that assigns to so this is to each stratified space X. We're supposed to get something in here, so that's a functor into vex. And this is easy. What it does is Well, you first there's a functor from that exit path category to the poset of non-negative integers, given just by looking at the given a point in here, you just inspect what the dimension of the stratum is. That gives you a non-negative number. And then there's another functor here that takes I to, or maybe I'll call it D, to RD. And it takes D less than D prime to the standard inclusion as the first coordinate, the first D coordinates. Okay? So now with that, then we can give a definition of error framing on a stratified space X is an equivalence of these functors between its tangent constructible bundle and this dim thing evaluated on an X. Maybe call that phi or something. This is an equivalence of functors from the exit path category to X. Let's see some examples. So one example is, so in the ordinary smooth case, I'll just put check. So this is, if X was just a smooth manifold unstratified, then this is the usual notion of a framing. That's the first example. The next is, maybe this isn't an example, but more of a comment, is that of error framing on X, in particular, determines a framing of the tangent bundle of each stratum. Determines a framing in the usual sense of T, a framing on X of P for every stratum on each stratum of X. But it's more data than that. It's not just the framing stratum-wise. There's some very specific interaction with the framings. And let me just illustrate that by drawing some pictures. So I guess I'll count these as more examples. So 1, 2, or whatever. So there you see a hemispherical stratification of the two disk. And I indicated with arrows what the Vera framing is. So note it's in particular framing stratum-wise. But also as you run this framing into the top, that first coordinate agrees with the first coordinate. Yeah. And I can modify this picture.
What was this last remark you say?
So yeah, so this framing, my thumb is the first direction. When I move this framing, I could contemplate the framing of the tangent space at a point. And when I move that point to the northern hemisphere, that first direction agrees with the given framing of that part of the sphere. So I a priori could have, look, that's a stratum-wise framing, but this does not count as a Vera framing because it violates that rule. And there's two choices for how to correct that, or actually an integer's worth of choices for how to correct that. And you can calculate explicitly what the space of Vera framings on a stratified space is, which would be maybe an exercise session type thing. So there's another, I just drew another stratified space with a Vera framing. And in general, it's convenient to just use the blackboard framing. So if I draw a kinked picture, then just take the blackboard framing. So for example, I won't draw the arrows because it's a waste of my time. That's an example of here's two different variframings on the same stratified space. Okay? The way I drew it in the blackboard, those are not equal as stratified, as variframed.
Sorry, I don't understand the picture. How does this line, what does it have to do with the framing?
Yeah, so abstractly, this is just some stratified space. And I drew the line so that if you, this picture inherits a variframing from the blackboard. So I could put arrows on this system now, like this, because of how I drew it in the blackboard. I could put arrows on this system, likewise. And you see, these are not the same variframings on what is the same underlying stratified space, exactly because of that slant. I don't know what to say. Help me out.
I'm already struggling with that picture, and I did struggle so also when you're talking about Wolfram. I mean,
Okay.
when you say, the blackboard framing,
Yes.
I mean, the thing is in the blackboard, so
Yes.
extension bundle is essentially already trivial. We're taking that obvious trivialization.
Okay. So there's
Or
a
taking
so that's like the trivial. So this is the tangent constructible bundle.
Yes.
So this is not, just the restriction of the tangent bundle. On the open part, that's right.
The
Perfect.
trivialization it already comes with.
Perfect.
But then why are you saying that when you run to the top, the first vector, if you run somewhere not on the maximum or the minimum, it's something I'm missing. It seems like it's not the first coordinate vector that you're getting.
So one thing is,
Go ahead. Here.
when you run that picture of 1 and 2, this vertically upwards,
Yes.
and you hit that horizontal arrow,
Yes.
You should think of that as an inclusion of that horizontal arrow into the 1, 2 coordinate system.
Okay.
And that inclusion of the horizontal arrow is precisely the inclusion of the arrow 1.
Okay.
And that's what David means by the inclusion of the first coordinate. And now, one thing misleading is these slanted lines. I don't think the word blackboard framing is enough to say what directions the arrows are in precisely.
Mm-hmm.
Once you get those framings to slanted lines, then David's claim is these are isomorphic as stratified spaces, but not as framed or variframed stratified spaces.
Yes.
So is this because one way you go so and then backwards to the arrow, and then there you follow the arrow? Is that the point? If I have a certain homeomorphism or isomorphism of stratified spaces,
Yes.
but if I go this way, I run that backwards and then I run
Yes.
left.
Yeah. Yeah. That's right.
You put this with your figure for the ones that you see went this way or that way?
Yeah. So if there was an isomorphism of these pictures, then in particular, I could restrict that isomorphism to that substratified space that goes like this. And there on that substratified space, abstractly, it's this variframing on that thing, whereas it doesn't agree on that one.
But if you turn it upside down,
So there, that is ignoring the framing on these pieces, and that would mess those up. Okay.
does this mean somehow that you have this parallel framing with respect to the flat framing with respect to that parallel transport function?
So on each stratum, yes, but then
When you go from stratum
then it's inclusion of the standard first coordinates. That's what parallel transport does. So here's.
I'm still struggling with that picture. How, when you go to the corner, how can you make both this be the first coordinate and this?
Yeah,
and still
so
consistent?
it can't be continuous, right? But there's a stratum there. The top and bottom don't lie on the same connected component of the stratum. So all you have to say there is that this is the inclusion of the zero vector, or the zero vector space into there, and that's always valid. So here's a fact that kind of gets at, is that every framed smooth manifold admits a variframed refinement. So given a framing on a smooth manifold, you can chop that manifold up a bunch and choose framing stratum-wise in this compatible way and obtain a variframed refinement. This is like a transversality argument.
But why don't you just stick to the manifold you have at the beginning?
You mean every refinement is different?
Oh,
The manifold already is very friendly.
oh, yeah, thanks. Yeah, every refinement of a, thanks, Hero, of a framed manifold can be further refined to have a Vera framing. Yes, definitely. So for example, take the 3-sphere with a choice of parallelization of it, and take the equatorial 2-sphere. That's a refinement of the 3-sphere, but that clearly cannot admit a Vera framing because the 2-sphere doesn't have a framing at all. But you can chop everything up so that it works out.
What do you mean with transversality for all things?
Yeah, if you don't mind, let me just, that's an indication of how you would go about showing this. It's a point set. It's a, just take that impressionistically if I'm okay.
You mean for like a sequence of grass lines that you might imagine defining?
Exactly, yeah. Yeah, so this is filtered by smaller orthogonal groups and stuff. Okay. So I've said what a Vera-framed stratified space is, but I want to have a category of Vera-framed stratified spaces. Not just with respect to open embeddings, that's not so bad, but I want this to be like Bun, where you have these exotic maps between stratified spaces, these 4 classes of maps. And I want a Vera-framed version of that. So to that end, let's first note that given a constructible bundle, then we can look at the vertical tangent constructible bundle. And what that is x vertical. Define it as the kernel of the differential of pi. As usual. And this is kernel of functors to curly vect. And likewise, there's epsilon x vertical dimension, which is, you could just say it simply as it reports at every point in k or in x a trivial bundle whose rank is the dimension of the stratum in that fiber that it lies in. So that prepares us to define finally this category of Vera-framed n-manifolds with these exotic maps. The vertical tangent constructible bundle. It specializes to the vertical tangent bundle.
So for the 2-sphere inside the 3-sphere, you need to add a circle to the 2-sphere?
Yeah, a priori you would just chop it up as some triangulation, but that's right. Okay, so definition. The infinity category over bun less than or equal to n, which is this thing, is that for which I'll tell you what a k point of this stack on stratified space is over a k point of that. For which, for each k point of this, which is a map from exit of k into bun less than or equal to n. And remember, such a thing is the data of a constructible bundle. So that's the data of a k point of this, where there's this fiber dimension restriction. Then I can tell you what a lift of that k point of this is. So that's the thing classifying x to k. And over here we have, so the data of a lift, so the space of lifts is identified with, and this gives a definition. This space exit of x mapping by epsilon v dim comma theta v. So these are two different functors from exit of x to vect. So together they give a functor to vect cross vect. And mapping to vect cross vect is vect by the diagonal. So the space of lifts here is defined to be the space of lifts there. Oh, certainly, yeah. So if vect happened to be a space, then the fiber of this is the loop, call it X, or, well, the fiber of this is the loop space of.
This lift isn't just a commutative diagram.
Well, it is in infinity categories, yeah.
I'm just saying, if you took an operator, in
Nothing
case
else you could possibly say?
There's nothing, yeah.
I'm just trying to make a comment.
Yeah, you got it, yeah.
I'm just trying to make a comment for like people who
That's
don't
right.
this commutative diagram honestly.
That's right.
My job to make it.
Yeah. So if x happened to be a point, pretend, and this plucks out two different vector spaces, then a lift is the data. It's data of an isomorphism between those vector spaces. That's, I think. Yeah, thanks, Hiro. So that's this. That's the category of variframed n-manifolds. So an object of this category is just a variframed n-manifold, but the morphisms are constructible bundles with a fiberwise variframing. That's all this is saying. Oh, I just said, so, and
Sorry, are these equivalent
as
as spaces or equivalent as infinity categories?
spaces. Yeah. So, you know, I don't count this as totally precise. You can see really what's happening is this is like I'm defining this in terms of a right adjoint of something. But I think this is better than describing it that way to understand something. So, and then likewise, so that's that, and then there's also this modification of it, which is nothing other than just the pullback C-bun. So that defines that thing. So it's just the compact manifold version. No embeddings. Okay. Now here's the reason that variframings are relevant for this story. I don't know if I'll ever use that space. Theorem is that there is a fully faithful functor Oh, yeah, it's a pullback. There's a fully faithful functor. I'll give it some notation. It's sort of like geometric realization, I guess. I'm not a huge fan of that notation personally, but I have co-authors that like it. From a category theta n op, if you know what that is, into here. Joyal's thing. So that I didn't even think was true for a while. So that this is an ordinary category. This is an infinity category. We started with this totally huge exotic category bun, and we put some tangential structure on it and so forth. And what's left, whatever this essential image is then an ordinary category as well. So let me explain the idea, and I want to hear comments. Should I say a word on what theta n is, or just proceed? Okay. Maybe I'll try to use this space. Theta 0 is defined as points. It's an inductive definition. And just to parallel, yes.
Is it okay to think of bun as some sort of thing that I get from stratified spaces by referring to certain kind of morphisms and then reversing the order of certain morphisms?
So yeah, that was my Burnside comment. That seems right, but it's not right. So that thing that if you try to go along those lines, you can construct a category, a Burnside category, where the backwards arrows are proper constructible maps and the forward arrows are open maps, so combination of refinements and open embeddings. That Burnside category exists, which is not, you have to show that pullbacks exist for proper or for constructible bundles. That's part of the hard part. But that maps sort of surjectively onto bun. It's not an equivalence. That's how we prove that this is an infinity category, in fact, is using that. That way you can guarantee horn fillers sort of.
We're missing some relations, is that what you're saying? Can we just
Yes, the Burnside category puts some relations. So the Burnside category is naturally a 2 category. And if you restrict the 2 morphisms to just be refinements and then localize on those, you get an ordinary 1 category, and that's bun. So it's some interesting localization of a Burnside 2 category. But that's not how we wrote an infinity 1 category. Yeah. Okay, so theta, and whatever theta n is, it projects onto delta op. So I'm defining it for you, and it'll be a category over delta op. I'll tell you what a lift of a, so the data of a lift like that is, this is a definition. Really, this is a right adjoint construction type thing, is identified as a functor from K cross over base finite sets. I'll explain this in a second, I suppose. With doubly base finite sets into theta n minus 1 op. Where what's going on here. So here I'm using that delta op maps to base finite sets. So any such map is just a base simplicial set, and it's delta 1 mod the boundary of delta 1. So it's this model for the simplicial circle, that thereby giving meaning to K mapping to base finite sets. And then this is just doubly based finite sets, where so the two different base points are different, and it projects in an obvious way onto just base finite sets by forgetting one of the base points. So that gives everything you need to know. That defines this category. What? Where? Nothing I said was strict, yeah. This is, all these diagrams are happening in infinity categories. Well, it turns out to be a 1 category. So, you know, it can be a condition whether an infinity category, all its HOMs are 0 types. And that turns out to be satisfied. So here's the idea for this fully faithfulness of this. Let me tell you first when n equals 1, and then I'm going to say like nothing about the higher version. So for n equals 1, then in that case, if you look at this, theta 0 is a point, so theta 1 is just delta. So theta 1 op is the same category as delta op. So I'm asserting when n equals 1 that there's a fully faithful embedding of delta op into this category of compact variframed 1 manifolds. And how it goes is I'll just draw some pictures. So that's an object of delta, and I'll assign to that object the variframed 1 manifold you can imagine. It's an interval with a bunch of dots on it, p plus 1 dots, and it's equipped with the upward variframing. Okay? So that's what the assignment is on objects. And on morphisms, so given a morphism, tau, from P to Q in delta, the opposite in delta op, then we assign to this, we can look at, so we assign to this, I'll just say it and then draw a picture for it, the mapping cylinder on this, if you just regard everything as sets, but it's this reverse mapping cylinder on tau, and you built it so that it lies over delta 1. It's that, equipped with the upward variframing. Let me draw a picture. So if tau was this map, so I hope you see that as a map in delta. We assign to that. I'm supposed to give you a map in Bun between these shapes. With the upward variframing, you can see this is organized as a constructible bundle over the 1 simplex. I hope you can appreciate what Bun is all about, because look, already you can describe things like this as morphisms in this geometric category with upward variframing. So notice a few things. Look, there's this aspect of this morphism. That's accounting for the closed morphisms. Here we see that dot disappearing. That's a refinement. here we see a dot getting created, anti-colliding. That's a creation morphism. So it's all there in this picture. And now, is the what?
This two-dimensional stuff, the shaded? Because you said earlier you take the mapping cylinder between these SNFs of sets.
Oh, sorry. It's like, yeah, I shouldn't have called it that. It's like the mappings. Yeah, I introduced some additional stuff. Is that what you're commenting on?
Or just the two-dimensional stuff?
Yeah. So you can just construct this explicitly, and I called it a mapping cylinder, but that's inappropriate, as you're pointing out. Yeah. It's just an explicit construction. Oh, yes, tell me about it. So the Joyal's geometric realization takes values in spaces.
Yeah, but
And this.
spaces, right? These manifolds.
Oh yeah, and it's way off from that.
Yeah.
It's so not that.
Yeah, that's what it seems to me. So could you maybe draw a picture of the realization of something bigger too?
It's exactly the pasting diagram. That it's
like lying flat, not
yeah.
flat as okay.
It's taking the pasting diagram literally as a topological space. Let me just make a comment that this whole thing is not true without the variframing. Because look, even in the simplest case, that's in the image of this thing for n equals 1. That's the value of on bracket 1. And here's a morphism in bun less than or equal to 1 if I ignore framing stuff. Do you see that's this valley that gets really narrow. It's the southern Utah Valley. So look, that's a morphism from an interval to another interval. And that's just not happening inside of delta. This isn't in the image. So, but the problem is that this morphism is not, there is no vertical variframing on it. So this does not admit a variframing, and as it shouldn't if that theorem were to be true. But I want you to maybe store this away, because this does lie in fiberwise in a two-dimensional vector space, which is just R2 and has a framing on the ambient two-dimensional vector space. And this picture has something to do with assigning to a morphism the composition of it with an adjoint, ultimately. So I hope I just want to wet your, so by relaxing this structure of a variframing, you start to see adjunctions happening. Just a comment for now. So now for n general, let me just say what the key is. So for n general, so you just take, the image is just the pasting diagram itself. So it takes an object t in theta n, and it assigns to it, it's the pasting diagram. So for example, bracket 1, if you know that notation, goes to the hemispherical stratification with the blackboard framing. Now the key for this to be fully faithful, well, in particular, that means automorphisms of the n cell in theta n, which are trivial, those are sent to, so that means that the automorphisms of the variframed n disk have to be trivial. So that, like, the framed automorphisms of Rn are trivial. That space is contractible. But it's just wildly not true that diffeomorphisms of the closed end disk as a frame thing is contractible. So this really, really uses the stratifications that are allowed here. So the key is that OT in theta n of the n cell, which that's just trivial. This, whatever this map is that I haven't exactly told you about, this is happening in this is the hemispherically stratified n disk with a standard variframing. So this means that this has to be contractible. And so you have to show this. It all comes down to showing this. And this follows by flowing vector fields. So this is, I hope you see it as surprising. It's canceling pseudo-isotopy issues that otherwise might have come up. So this is by flowing vector fields. So this is like down in there deep. Once you have this, then everything else kind of unfolds. And you can imagine a variframed automorphism of this n disk. Well, what you can get from that is you can blow up the two zero-dimensional, like the north and south pole, to have a n-1 disk cross an interval, and everything's variframed. So a priori, you would have just had an automorphism of n-1 disk cross interval, which is like a pseudo-isotopy of the n-1 disk. But this thing has a vector field on it, flowing by which shows that automorphism has to come from just the variframed automorphism of the n-1 disk. And by induction, that's trivial. That's how this goes. That's why the variframing. OK. Wow. Oh, I better get there. OK, I'm gonna pick up the pace a little, just so I can at least state the theorem. So definition is so that is the smallest. That's a C. Full subcategory, infinity subcategory, such that three things happen. One is that each of these is in here. The -1 case is when that's empty. Two is, well, I said three things, and I'm going to put them into the spirit of being faster. If we're ever given a pullback diagram, so this is pullback, thanks, in which that's a closed map. So it's the opposite of closed inclusion, and that's a closed map. And this, too, is a closed map slash a refinement. And that's a closed map slash refinement. So if you're given one of these, where these three terms lie in this category, then that one does. If those are in there, then that implies that M is in there. That defines this category. It's the smallest one containing these disks that are closed under these formations. So let me illustrate this with two pictures. So one picture is if you take the all purely closed version, and so let's argue that that thing is in here. Well, actually, this won't be a complete argument of that, but you can see these kinds of shapes. So that's a pullback in this category. And this is a triangle with a certain variframing on it. So is that. And that's an interval with the variframing. And because you can piece those together to form this thing, that means that this thing is also in there once you know that these triangles are in there. And then to see that the triangles type things can be there, here's the closed refinement version of this. So you get the triangles essentially once you have pictures like this. So that's another pullback. And look, so these horizontal ones, this refines away that top dot, and so does this. These just are the opposite of a closed inclusion. That's a pullback diagram. These three things are in disk, therefore that is. So disk is being defined just by, in terms of generators. And the relations come just from those that are already inside of the relations in manifold. Okay, fact that every framed n-manifold has a variframed disk refinement compact. It's another transversality argument together with triangulation stuff. These are not obvious facts. So now, another fact, or observation, is that this factors through this category of disks. Because you can build every pasting diagram just by these simple gluing operations from cells. So this then gives a restricted Yoneda functor. Notice the pattern from what was happening earlier. Because of this op, it'll be contravariant on theta n. And theorem is that this functor, this factors as a fully faithful functor of infinity categories. I'll call it frac C because it's like category from C disk into cat infinity n. So infinity n categories can be modeled as, so here I'm taking it incarnated as complete Siegel theta n spaces. Just like exit. And it's given explicitly by, just like exit, probing a general distratified manifold M by theta n. Geometric realization of T. But the probe is happening in the opposite direction. Now here's let me just say this in words. Well, let me say the next result, and I'll say that in words. This theorem is this factors as an equivalence of infinity categories. Oh, whoops. Before I say this, therefore, we get, it's this trick. You do it again. We get a restricted Yoneda functor from infinity n categories to pre-sheaves on C disk. So there's a map from cat infinity n to pre-sheave to functors from C disk n variframed to spaces, just by restricted Yoneda type thing. And this is given by sending, C, an infinity n category, to the assignments that sends to every distratified variframed n manifold the space of functors between this frac C of M and C. And this, if you think about what this is the space of C labels of that distratified manifold. So like I draw these pictures, and that's an M, a variframed M, and a point in this space for a fixed curly C is a way of decorating this by morphisms in C, I or something, all the dots by objects, and then all the cells by two morphisms. So this looks very much like the blob homology type pictures, which was much of the inspiration for these constructions. And the theorem, this is crappy board work. The theorem is that this functor factors as an equivalence as closed sheaves on disk. So this is the full subcategory, and I'll put also there complete, because the completeness is such an unnatural condition. You just put that in for the ride. But the complete ones are those that send. The closed sheaves are those co-pre-sheaves on this category that send the diagrams as in 2 to pullbacks, that carry 2 to pullbacks. Those are the closed sheaves. So note that if you remove all of the positive codimensional strata, these kinds of pullbacks, the closed ones, are just joint unions. So these closed sheaves are some multi-object version of symmetric monoidal functors from manifolds to spaces. So this is, again, a lot of the inspiration with thinking of some of these ideas. The closedness condition on functors to spaces is a multi-object version of symmetric monoidal. What? Complete. Yeah. You just put that in. Oops. Factors as an equivalence. So that's an equivalence. So you completely identify infinity n category exactly as the labeling systems on n categories. So let me just say, and I won't write down because it takes too many words and I'm not going to justify it anyway, is that to prove this, so that you know that it lands in here is very easy. To know that it's an equivalence, you have to know that frac C sends these kind of diagrams to push-out diagrams in infinity n categories. So good luck computing push-outs among infinity n categories. But there's a trick, is it turns out frac C is, frac C of M, you can obtain it as, wherever it is. Did I define that? Yeah. You can obtain it as a localization of the exit path category of M inside of a lax version of n categories. And just by inspection, exit path categories have the right push-out property, and therefore, so does frac C. That took us forever to find a way to prove that. And it's a technique that I think is interesting. If you want to show a diagram as push-out among infinity n categories, if you know that those can be obtained as localizations of 1 categories, for which it's manifestly a push-out, then you're done. It's a really nice trick.
Why does localization preserve push-out?
It's a left adjoint construction. It's defined in terms of homming out. Okay. I think I can finish. Okay, pressing forward. Definition, finally. Factorization homology is the functor so of 1 categories, or of infinity categories. Where you, I'll separate it out a little bit. This could be made more concise. That sits inside of there fully as complete Siegel theta n spaces. And this, by right con extension, goes right con extension along that thing I just erased, the comparison between theta n op and C disk, to functors from C disk n variframed spaces, followed by left con extension to functors from C manifold variframed to spaces. So that's factorization homology. This I think of as this right con extension is like extending sheaves from a basis. So if you have an invariant of rings, you can extend that to an invariant of schemes kind of thing. And this left con extension is like averaging over all disk refinements. Integrate over disk refinements, variframed disk refinements over a manifold. So inside of here is a regular, smooth, framed, and manifold. So you get invariants of such things in this way from infinity n categories. And then I'm not going to say anything about it because of time, there's the pointed version, where I remove the C and have pointed categories. I had in mind using, you can tell me if you see blue, if you don't. Can you see this? Yeah. So it's pointed infinity n categories, and you just get rid of that thing, the C, and you get rid of that thing. And that's also, and there's, I called it a theorem. That's a definition. To manage the non-compact stuff amounts to another wrangling of pseudo-isotopy type issues, where again you use the veriframing stuff. You have to manage the pseudo-isotopies in 3 places in all this story. So theorem is that this functor, it and its pointed version, is fully faithful. So this embeds infinity n categories as certain kinds of invariance of framed n manifolds. That and the pointed version, both. Yeah. What? So yes, but honestly, so the hardest thing, you have to show that C disk n is sifted as a category, which is an extremely hard thing to show. But I'll say the answer is, or should be, once we sort out those details, which are substantial, is that it's closed sheaves. It's those that preserve those kind of covering things that satisfy excision. But to even state excision is kind of complicated. You have to show this satisfies push forward and stuff. Remark. So first, some examples. So factorization homology over dk of an infinity n category is nothing other than the space of k-morphisms in C. Okay. Likewise, for this pointed version, so C is pointed in order to do the non-compact version. This is the space of k endomorphisms in C of the, I'll call it the unit, but it's of the distinguished object. Another example is when n equals 1 over the circle, this is the Hochschild space of C, which it's like if you choose a CW decomposition kind of thing, is the geometric realization of the cyclic nerve of C. But purely, it has the S1 action just by construction. Let me make some more remarks. Remarks is that, first, there's an enriched version of this, which is by far more interesting. But it's, to set up is just more complicated than is worthwhile doing in a thing like this. So there is an enriched version. So think like linear version. Pick a symmetric monodal category, for instance, and you could look at infinity n categories enriched over that and contemplate not functors the spaces, but I'll just say functors to that thing you're enriching in, but you need to chain complex.
So for infinity n categories is rich in symmetric monodal infinity categories. What kind of formalism would you actually use?
There is one David Gepner and Runa, they have this. Well, yeah. So we make our own that is convenient for these methods, sort of along the lines of, yeah. The techniques. Yeah, so this is set up so that it easily accommodates an enriched version. So instead of, yeah, and it's also convenient to contemplate enrichment in much more general things so that, like, there's the identity enrichment and stuff.
In the left, you can enrich in something, and there you just change spaces by whatever you enrich.
I'll say yes, but so it's more like sections of something you build over this. Okay. So this diagram commutes. So you can take the n-fold d-loop of an En space to get an infinity n category pointed. You can take factorization homology to get land inside of functors to spaces, as just explained. Another story that probably more of you are familiar with is you can take factorization homology. Notice the L, that makes all the difference. So this is the regular category of n-manifolds and open embeddings that you know. Infinity 1 category. Yeah. And so it turns out there's a full, that goes into there fully faithfully, because there's a localization on veriframe n-manifolds where you just say a map is, so where you localize with respect to those maps that are equivalences on top dimensional strata. So then the local objects for that are those that have no top dimensional strata, which are just manifolds. And the closed sheaf thing turns into the symmetric monoidal thing. So here's factorization homology for En spaces, and this diagram commutes. So this generalizes the En story. And as Peter talked about, these have to do with perturbative field theories. These do not. So this new factorization homology with coefficients and something more general describes non-perturbative theories, ultimately. So I have two more remarks. One I just said, so one more. And this, I should have left the whole board for this because it's that important to me, but it'll have to be in this small space, which is that notice that you're getting invariance of manifolds with no dualizability assumptions on the category. So the manifold invariants that come up through this are not described as functors out of a Bordism category. So these invariants of n manifolds require no, or in practice little, dualizability.
It's really invariant of stratified manifolds.
That's right, and that's the so you can still get an invariant of ordinary manifolds by averaging over stratifications.
But if the diagram commutes, isn't it saying that the invariants for the ordinary manifolds are the ones that come from realizable stuff?
No. Oh, this commute, but this is not essentially surjective. So there's more things here in the image of this than there are in the image of this. This is a small part. And clearly, I didn't have time to say anything about the case with adjoints, where you can get it making this kind of assertion a little more precise. But there's a story where you relax veriframing to just regular framing, and there the relevant story is about infinity n categories with adjoints. In that story involves another piece of this that is among the hardest things I've been involved proving also, which when I think about how it's related to other works, it's sort of like an infinitesimal version of the frame function theorem. But I just don't have time to talk about that, I guess. So thanks a lot for your attention. I hope that if you come away with something from this, it's that that maybe you can find some good examples or get into it in some way. The theory is founded solidly. It's not like some hypothetical theory. So yeah, thanks. So variance on infinity n categories that correspond to variations of infinity n categories that correspond to invariance of manifolds with different kinds of structures. Is that the question? Thanks. Yeah, so definitely. In fact, you give me your favorite kind of stratified structure. It has to satisfy a certain kind of, I'll just say, siftedness criteria that many of them will. And then you have an appropriate notion of infinity n categories that has just not been considered. So it's not worth highlighting per se, but you get a different notion of infinity n categories where you have pivotalness of some kind or another. And the story works out very much the same. This is like the initial structure of error framing.
I have to admit that the whole thing was kind of overwhelming for me, but is there any connection between this factorization homology and the action of a field theory as defined in the sort of beta type now? Like, can you see that integral as we say, somehow as a factorization homology?
That's a wonderful question. So all I can do is speculate, and I think yes. But I need to learn more about that, and also that needs to be made more precise what the problem actually is. I hope that addresses your question.
Do you mind repeating the question?
So the integration that happens when like quantizing, like these Feynman integral type things, how is that related to factorization homology? Is that the question? And yeah, we're so optimistic. This is like this is a way of doing, field theories just through observables, kind of, because the pointed version is functorial with respect to open embeddings in particular and stuff. So this gives like an observable point of view on non-perturbative field theories, but it's brand new, and we haven't really made that connection.
So where are the observables?
So for the enriched version, the value of factorization homology should be interpreted as the observables of the field theory associated to C on that manifold. And I'm mostly interested in the case where the manifold is unstratified. And yeah.
But one should say this is the topological part of it. And
Yeah, thanks.
Bell and Owen William have a more geometric.
For the perturbative aspect. Yeah, thanks a lot. This will describe topological field theories, not like quantum field theories and very interesting Euclidean field theories, not that. I mean, of course, we dream that the methods can carry over, but that would require some new ideas.
Can you maybe just say in words how the modern categories describe this functor on your very framed manifolds and how you see its universal properties?
Yeah. So the board is my hypothesis? So, if there was more time, I could have talked about that. The tangle category is RK. It's the representable functor on this category, represented by RK. That's the tangle category of K tangles in N manifolds. Once you verify that, so this category was designed so that was true, so that you can compute the space of maps from RK to an N manifold, and it turns out to be nothing other than the space of N minus K dimensional properly embedded framed submanifolds of that manifold. That's the essential calculation from which the tangle hypothesis follows.
So does this give the, if you push it forward to the adjoint,
Yeah.
give a different tool for the borders and hypothesis?
I interpret that as the same question that was just asked, and I'll say yes.
Well, he's proving a more general bordism hypothesis where you have these singular manifolds. So if you go to the edge, the case where you have adjoints,
Uh-huh.
then you get to what people usually call the bordism.
Yeah, so two steps. You go to the case with the adjoints, and then you also have to, so the tangle hypothesis implies the bordism hypothesis. Okay, so through some kind of formal procedures, and you can prove the tangle hypothesis easily internal to this theory. And that's strictly for the case with adjoints. Yeah, I would love to write down a formula that makes that just so evident, but it would take like 10 minutes, and that could happen later. There's some advantage too. It gives you an explicit way of calculating the invariance, moderately explicit way of calculating the invariance of an n manifold from a fully dualizable object of an n category. It gives you an expression. It's not some implicit procedure only defined upon choosing a handle-body decomposition of a manifold. That's the formula I would write down.
So you could equally well take the sort of opposite of integration, where you think there's a function from various angles to completely non-linear vectors.
Okay.
Is that fully faithful, or does it works out? I suppose what I'm asking is it the case that somehow manifolds detect all of category theory? Somehow it's the same.
Stratified,
Is it
yeah.
the case that vice versa?
Well, yes, I guess, because yes. This is an equivalence, this arrow, to the closed sheaf part. And then Yoneda says that this embeds into Apprecia's fully faithfully. I don't know if that's what you're asking, if that was fully faithful, right?
Yeah, I don't know what it was. I guess I'm asking if I have two different manifolds, is there some category so that their factorization homology?
Okay, so that's a really interesting question. So is this a complete invariance of n manifolds? And I don't know, but I think, I don't know. So what's lurking in this excision proof would in particular give some kind of excision statement for diffeomorphism groups of manifolds, which I think is tantamount to that kind of question.
Do you know whether it distinguishes one spaces, for example?
Yes, easily. Yeah. Configuration spaces do. Or sorry, those two. Yeah, other people. Yeah, Paolo Salvatore and I forget. Aone. So, I'm sorry. Yeah, that's right. Just for using what other people have already done to construct invariance, then yes. I'm optimistic that Reidemeister torsion can be phrased as an invariance through factorization homology, but I haven't pursued that at all. Maybe one of you can. For the configuration space point of view, yes. But the Reidemeister torsion might be the way to go about this. Yeah, not for me.
Do you expect that requires the right-hand column in your diagram down here, or we can just be done with the end?
Which approach, the configuration approach or the Reidemeister?
Reidemeister.
I think that would be the other side.
Oh, yeah.
Yeah.
Okay, let me remind everyone we have another question session in the afternoon, and we will produce a new envelope. Somehow the envelope always seems to be gone. We have to get a new one. So we'll produce a new envelope also for anonymous questions, which we'll put up there. And also, we do want to have a proper break, so we'll start with the next talk at 10 past 11. And let's thank David for the